So hello students, welcome to our channel. In this session we are going to learn about analysis of binary search. So previous class we discussed about divide and conquer general method. Now we are going to discuss about how to solve the binary search using divide and conquer strategy. So after that we discuss the analysis of binary search. So first we discuss what is binary search. So binary search means you are going to give n records. So here we have n records which have been ordered by keys so that x1 less than x2, x2 less than x3 and so on, xn minus 1 less than xn. So this is the example here. The elements are minus 15, minus 6, 0, 7, 9, 23, 54, 82, 101. Here the x1 is less than x2, x2 is less than x3 and so on, xn minus 1 is less than xn. Okay. So when we are given an element x here, so what is x? X is searching element. X is searching element. Now binary search is used to find the corresponding element from the list. That means if I give the x equals to 9, now it returns 9 is at 5th position, 9 is in 5th position in the array. In case x represents, we have to determine a value j here. So what is j? The 9 is at location 5. Now it returns 5. That means that a of 5 equals to x. The searching element is 9. The a of 5 is 9. So it is successful search. If x is not in the list, then j is set to 0. That means it returns the function, the binary search function returns 0. That means it specifies it is unsuccessful search. That means if the number is in the list, then the number found in a particular position that will be returned. Otherwise it returns 0. 0 means the number not found in the list. So we solve this problem in two ways. One is iterative approach, another one is recursive approach. We have two approaches. In recursive approach we use divide and conquer strategy. So before that, so first we discuss about iterative approach. So let us take, so this is the array. Numbers are minus 15, minus 6, 0, 7, 9, 23, 54, 82, 101. So this is the input. So let us assume this is the array A and indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8. Now we are going to give the x value. X is for searching element. Okay. Now binary search a comma I comma l comma x. What is a here? A is array. A is array. What is I? I is starting index. What is starting index here? The starting index is 0. L is length of array. So what is the length of the array? The length of the array is 9. 0 to 8. So it is 9. And x is the searching element. The searching element is 101. Now we apply what is low here. Low equals to I. What is I? 0. High equals to L. What is L? 9. Now we enter into the loop. We check the condition low less than or equals to high. 0 less than or equals to 9. It is true. It is true. So we enter into the loop. Mid equals to low plus high by 2. 0 plus 9 by 2. So 0 plus 9 by 2 means it is 4. Okay. Now this is the mid. Now you compare, what is the x value here? X is 101 less than A of mid. What is A of mid? A of 4. A of 4 means 9. So 101 less than 9, it is false. So go to here. Else if you compare x greater than A of mid. So what is x here? 101 greater than A of 4. Yes, that is 9. A of 4 is 9. So it is true. It is true. So we update the low value. So what is low here? 0. Now low value equals to mid plus 1. That is, what is the mid value? 4. 4 plus 1 means 5. Now the new low value equals to 5. High equals to 9. Okay. Again you go to while. Compare low value 5. So what is the high value? 9. So 5 less than or equals to 9. This is true. Again, what is mid? Low plus high by 2. So what is low? 5 plus high 9. So 5 plus 9, 14 by 2, that equals to 7. Now this is the mid value. So this is the mid. Now again you compare. So what is the x value? 101 less than mid of 7, that is 82. No, it is false. Now you compare. So x greater than A of mid. 101 greater than 82. Yes, it is true. So again update the low value. What is low? 5. So low equals to mid plus 1. What is mid? 7. 7 plus 1 means now low equals to 8. Again we enter into the loop. You are going to perform mid value. Now 8 plus 9 by 2. That equals to 17 by 2. Again it is 8. Now this is the mid. Now this is the mid. Now you compare the 101 less than 101, false. 101 greater than 101, false. That means that we find the element in the array. So we return mid here. Okay. So what is the mid? 8. When we print, we represent as 8 plus 1. So the 101 found in 9th position. So next one is a recursive approach. So recursive approach means here we define a function binary search. This function calls the same function. That means the function calling itself is known as a recursive function. That means the binary search function calls the binary search function. That concept we call as recursive approach. We divide the problem into sub-problem until here the condition is it L equals to I. What is L? The length. So L represents length. So up to L equals to I, we are dividing the problem. Here you observe that this is the dividing the problem, the function calling itself. Now the same problem. So this is the array A. Supply, what is A here? So array I equals to 0, L equals to length of the array, that is 9, X equals to searching element. For example, the searching element is 82. Okay, here I am taking the searching element X equals to 82. Now, so L equals to I. What is L here? 9 equals to 0. No. So we move to L spot. In L spot, we are going to find the mid. Already we discussed how we find the mid. Mid equals to low plus high by 2. Here the low is I, high is L. So what is I value? 0. What is L value? 9. So total 0 plus 9, 9 by 2, that equals to 4. Now 0, 1, 2, 3, 4, 5, 6, 7, 8. Now 4. This is the mid. So this is I, this is L. Now you compare X. What is X here? 82 equals to A of mid. What is A of mid? 9. No, it is false. So next we check another condition, else if what is x? 82 less than A of mid means 9. Now it is also false. So we are going to here binary search. What is A? Array. What is mid? Mid value is 4. 4 plus 1 means 5. L is 9. X is searching element. Again we call the same function. Now, so this is the problem. Now this problem is divided into sub problem. Now this is the array 23, 54, 82, 101. Now, so this is the divide strategy. Now again apply. So what is A now? So this is the A. So these are the indexes 5, 6, 7, 8. So what is the I value? I equals to 5 now. What is L? L equals to 9. X equals to 82. Now you compare what is L here? 9 equals to 5. No. So go to else. Mid equals to I plus L by 2. What is mid now? I is 5. L means 9. That is 14 by 2. Now mid equals to 7. Now this is the mid. Now this is the mid. X, what is X? 82 equals to A of mid. A of 7 is 82. Yes, it is true. So we return the mid value. Okay. Now 82 is founded. When we print the position, we are going to increment the value by 1. So it returns 7 as output. So this is the binary search program in iterative approach. So this is the binary search program in recursive approach. So A is the array, I equals to 0, L equals to length of A minus 1, X equals to 1, 0, 1. We call the function binary search. Now if we give the input 101, it returns the output as element found at 9. Now how many comparisons we are doing here? How many comparisons? 4 comparisons. Now here I am taking one variable to represent the number of comparisons, C. Whenever I do comparison, I increment the C value, I print the C. Now if I give the input 101, the searching element is 101, the number of comparisons are 4. If I give number 101, the number of comparisons are 4. So similarly, if I give number minus 15, we get the comparisons of 3. For minus 6, we get the comparisons of 2. For 0, the minimum number of comparisons are 3. For 7, it is 4. For 9, it is 1. If it is 23, the number of comparisons are 3. 54, it is 2. 82, the number of comparisons are 3. If it is 101, the number of comparisons are 4. So this is the array, the elements in the array. Okay, we execute one more time. We give the input as minus 6 here. In the place of 101, we give minus 6. Now the number of comparisons are 2. So 1 comma 1 and 2 here. That means 2 represents the number of comparisons. Okay. If we give 0, the searching element is 0. Then it returns 3. So 1, 2, 3. Okay. If we give a number that not present in the list, 123, then also it gives the number of comparisons are 4. Okay, but element is not found. This is unsuccessful search. Okay. Now, so what is the average here? The average equals to the total number of comparisons. 3 plus 2 plus 3 plus 4 plus 1 plus 3 plus 2 plus 3 plus 4, that is 25. How many number of elements? 9. So this equals to 2.77. Okay. So that means if there is 9 numbers, the average comparisons are 2.77, and there are 10 possible ways that an unsuccessful search may terminate depending upon the x value. Now, for example, if I give the x value equals to minus 20, that is less than x1. Let us assume this is the x1, x2, x3 and so on. Now, x equals to minus 11. Now, the value lies between x1 and x2. That means x is greater than x1 and it is less than x2. This type of values are 10. 10 possible ways we have. X less than a of 1. In second, x is less than a of 2 and it is greater than a of 1. Another case, maybe x less than a of 3 and it is greater than a of 2, and x is less than a of 4 and it is greater than a of 3, and so on. We are going to get 10 possible ways to get unsuccessful search. So each time this x less than a of 1. So for that we are going to compare 3 comparisons. We are going to do 3, and for this we are going to compare 3 comparisons. For next one also we are going to do 3 comparisons. For all the 10 values, 10 possible ways we are going to do these type of comparisons. So there is 10 possible ways. Now, if you add all these numbers, we get 34 by 10. That is 3.4. 3.4. That means for successful search, the minimum comparisons are 2.77. For unsuccessful search, the minimum comparisons are 3.4. Okay. So, the time complexity for the successful search is big O of log n. Okay, why? If the n is 9, we get the value 2.7. So, we represent that as a log n. Similarly, for unsuccessful search also, the numbers are 9, the minimum number of comparisons are 3.4. That means log n. 4. So, for successful search and unsuccessful search, in both the cases, we get the time complexity as big O of log n and log n. Here, best case. So, what is the best case? If the searching element is found in first iteration, in first comparison, the time complexity we are expressed as big O of 1. That means, in first iteration only you get the searching element. That means you search the element that is A of mid. And for average case, the time complexity is big O of log n. For worst case, maybe the element is we found in last comparison or the element not found in the list, then also the time complexity is big O of log n. So now we are going to do analysis for worst case. Let T of n be the time complexity of the binary search. Here we are finding the value based on the mid. So what is the mid here? Mid equals to n plus 1 by 2. That means we divide the array into 2 parts, n plus 1 by 2. So therefore, the T of 0, if you give the n value, then the time complexity is 0, and T of n equals to 1. When it becomes 1, if the searching element x equals to A of mid. That means this is the best case. Otherwise, 1 plus T of n plus 1 by 2 minus 1 if x less than A of mid. Otherwise, 1 plus T of n minus n plus 1 by 2 if x greater than A of mid. Okay, so what it is? This is the array. Let us assume this is the array. Now, so what is the mid? N plus 1 by 2. So let us assume, so this is the mid value. Now, if the x equals to A of mid, then T of n equals to 1. That is the best case. Now here we are doing worst case analysis. Worst case analysis. Now, so let us assume n equals to 2 power k minus 1. So k is a non-negative integer. Now, so this is the 2 power k into 1. The remaining part is 2 power k minus 1, and here another part 2 power k minus 1. Okay. Now this is the one part. So this is the mid. The remaining part is 2 power k minus 1, and the another one is 2 power k minus 1. Now, so what is mid value? N plus 1 by 2. Now what is n? 2 power k minus 1. So 2 power k minus 1 plus 1 by 2, that equals to 2 power k minus 1 for k greater than or equals to 1. Now they are giving, so t of 0 equals to 0, t of n equals to 1. Here I write the same, t of 0 equals to 0, t of n, what is n here? 2 power k minus 1 equals to 1 if x equals to a of mid and it equals to 1 plus t of 2 power k minus 1 minus 1 if x less than a of mid, and it becomes 1 plus t of 2k minus 1 minus 1 if x greater than a of mid. Okay. In the worst case, x equals to a of mid is always fail. That is the worst case. Here we are doing worst case analysis. Worst case analysis means maybe the element we found at the last comparison or element we don't found. These two are the worst cases. So we consider worst case of 0 equals to 0, worst case of 2 power k minus 1 equals to 1 plus w of 2 power k minus 1. So this is now solved by repeated substitution method. Already we discussed in our previous class. Here, so w of 2 power k minus 1 equals to 1 plus w of 2 power k minus 1 minus 1. Repetitive substitution. That means in the place of w 2 power k minus 1, we are going to substitute. We get 1 plus, again 1 plus w of 2 power k minus 2 minus 1. Now we are going to find w of 2 power k minus 2, that we are going to substitute. We get the 1 plus, so w of 2 power k minus 3 minus 1. Okay. If we repeat this until it becomes I. What is I? Number of ones here. Here the number of ones are 3, it is 3. So we replace the number of ones with I plus w of 2 power k minus I minus 1. Okay. So now we repeat this until this becomes 0. So when it becomes 0, if I equals to k, then the w of 0 becomes 0. So substitute here I equals to k plus, so w of 2 power k minus k, 0 minus 1, that equals to k plus w of 2 power 0 is 1, 1 minus 1, 0, k plus w of 0 equals to 0, that equals to k here. But so 2 power k minus 1 equals to n. So what is k? So k equals to log 2 n plus 1. So we write, so W of n equals to log 2 n plus 1 equals to big O of log n. Okay, so this is the worst case analysis of binary search. So next class we are going to analyze quicksort. Thank you.